We'll proceed with the last talk of today, and it's a real privilege for us to have Professor Jean-Marie Lehn. Professor Lehn is a professor at the University of Strasbourg and the Institute of Advanced Study in France. He is well known for receiving the Nobel Prize in 1987 for his synthesis of cryptans, which pioneered what we call today the field of supramolecular chemistry. Professor Lehn is considered to all of us the father of the field, which intrinsically extends to the field of dynamic chemistry as we know and extensively use it today in polymer science. And of course, today he's going to talk to us about dynamers and adaptamers towards dynamic and adaptive functional polymers. Professor Lehn, thank you so much for accepting the invitation. It's really a privilege for us. And may I ask you if you can record your talk?
Yeah, sure, you can go.
Thank you. We are looking forward. Thank you. Thank you. We're looking forward to your talk.
So, thank you very much for the invitation first, because, you know, they have learned COVID at least has done one thing. It has made us much more comfortable with using these online meetings, which means that now we can talk to anybody around the world at a certain moment. It's quite fantastic. No, of course, everybody says that, but it's always nice to realize it really in practice. Of course, it's still nicer to see each other from close by. It's quite interesting. So thank you. I was in touch mostly with Professor Filipov. He organized the thing and invited me, and it took some time to find a good day, but finally we found it. So that's quite good. So I will let you know now about some of the more recent things we have been doing in the field of dynamic polymers. I will start quite early on, just to give an idea about what we have now. I have to split the screen. Just a second. You see it?
That's fine. Thank you. Yes.
Okay. So, as I said, online conference. And the title, which you just mentioned, is Dynamers, Adaptamers. They're just names which have been produced by combining dynamics or adaptation with polymers. And I will describe some of the things we have been doing along the years. So all of you know what molecular chemistry is. From the atom, you make molecules using strong bonds. And then beyond these molecular structures, as molecular compounds, they interact. And our chemistry has been developing, which is really try to understand what happens beyond the molecule, assemblies, non-covalent interactions, and mastering how to organize molecular assemblies. This was work we have been doing for many years now. It started in the 1960s, and it has developed enormously. So the basis there is not a chemical reaction, as of course all of you realize. For molecular chemistry, the important thing is a chemical reaction. For supramolecular chemistry, the basic property is a physical non-covalent interaction. That's something which chemists have to realize, that in supramolecular chemistry, the basic processes of transforming the type of entities of supramolecular nature is a physical interaction, not a chemical reaction. And we will see we can combine both of them. Now, maybe some chemists won't like that, but that's the way it is. So let me also put the pointer. This supramolecular chemistry is a dynamic chemistry. There is a property which hadn't been recognized from the start. It took some time to realize that supramolecular objects are dynamic. That means they can fall apart, dissociate into their molecules, reassociate, and in doing so, exchange also the pieces. So this is a dynamic non-covalent chemistry. The non-covalent object dissociates into the molecules of which it is formed, which then can undergo changes, exchanges, and so on. And this is a dynamic non-covalent chemistry. Now, if you want to import that into molecular chemistry, there is something you can do is to introduce reversible covalent bonds. That means also bonds which can break and reform. And this then leads to dynamic covalent chemistry, which we'll see examples. And then I've thought that, okay, but I can put all these two areas, the covalent and the non-covalent, under the same heading by calling it constitutional dynamic chemistry, stressing the fact that it's the constitution, the way the chemical object is built up, the constitution of the chemical object, that becomes dynamic, where it can fall into pieces, dissociate and reassociate either on the molecular or on the supramolecular level. And of course, if in the meantime, as these things proceed, some agent is applied to this section, to this assembly, then things may change and make the assembly adapt to the entity which is under this agent. For instance, we heard about pressure early on. In fact, we never tried pressure. I thought, when I heard about pressure, I thought, okay, maybe I should also try pressure. But it's quite obvious that when you change conditions, the medium, for instance, you get an adaptation of your object, your chemical dynamic object, to this agent which has been applied. And this leads then to what we now mostly do, adaptive chemistry, and you will see why we do that. And the result of developing adaptive chemistry, one, let's say, subheading, area is materials. Now, let's me first look at a given class of materials, which are the ones we are concerned about today, which is polymers. And this can then be called DYNAMERS, dynamic polymers, which can be of two types. Either the monomeric entities polycondense through a reversible chemical reaction and then lead to molecular covalent dynamic polymers, molecular covalent dynamers, where the monomers and for instance here, one monomer, a bifunctional monomer, and another difunctional monomer, bearing complementary reactive groups. That means groups which can undergo a reaction which is reversible. Then they form this chain, a long chain. In this case, it's chain-like, also others. And this then leads to a dynamic covalent polymer. On the other hand, if it is not a polycondensation, but a polyassociation through non-covalent interactions, through taking into account, of course, the way they interact, it means the interactional recognition, this leads to supramolecular non-covalent dynamers. And then, in that case, the yellow pieces and the red pieces are complementary molecular groups which can connect together through recognition processes. And that's what I want to start with, because I wanted first to start with supramolecular polymer chemistry. Of course, molecular polymer chemistry is known for many, many, many years. Supramolecular polymer chemistry is much younger than that. So let's start with that. In order to make linear main chain supramolecular polymers, what we need is two monomers, two molecular monomers, like this one shown here. It's a bit complicated, but for some reason we used it because it's a derivative of tartaric acid, which can be made rather soluble by putting long chains C12H25 on the OHs of the tartaric acid, and then functionalizing on through the carboxyl groups by recognition groups, which are here. derivative of pyridine with a donating hydrogen bond donating group and accepting and a donating group. The complement to that is a derivative of uracil, which is one of the nucleobases from nucleic acids. And they have this one has derived from uracil, has here an electron and hydrogen bond acceptor, hydrogen bond donor, hydrogen bond acceptor. So DAD, ADA are complementary. So when you mix them, they can undergo a triple hydrogen bonding interaction, which then keeps the chain together and makes out of these molecular monomers the supramolecular polymer. You see here also that the starting materials are both solids, whereas simply mixing them leads to a liquid crystal. And here you see electron microscopy of the object obtained. We come back to that. And I would also like to stress, we heard it in a previous lecture, I saw the name, Bert Meyer, a very good friend, he has contributed enormously to this area with a specific type of interaction, UP, it's called. And interestingly also, the simple mixing of these molecular pieces leads to a new property, which is here, a liquid crystal. Now, this work we did in 1990, it was in fact the first paper on the supramolecular polymers, but the date is important, 1990, you will see that in a moment, why. Now, it is not finished at that stage because we can now look into more detail into these supramolecular polymers. The monomers are complementary units, as we just saw. Beyond that, they form, as we also saw, a supramolecular polymer chain. But it doesn't stop there. You can then analyze the material obtained, as has been done by scattering, X-ray scattering data, which reveal that, in fact, it's a triple helix, a triple strand, a cylindrical object contained, made of three strands, three supramolecular strands, and with the long chains, which make it in fact soluble, C2H25 sticking out of the cylinder. The core is about 15 angstroms, and the whole thing with the side chains is about 40. Now, these chains, of course, can entangle so that it goes one step further, which is one can then, by entangling of the side chains, form these fibrils, bilateral association. And this is then going from the nanoscale, the molecules, to the microscale, these long fibers. Now, there are other types also of supramolecular polymers, and one is shown here. This is just one we did, but there are others. You will see others, in fact, in the rest of the talk. This is this dihydroxide, which can undergo a tautomerism, and the tautomerism provides ways of linking by hydrogen bonding three of those units. And then this is a sort of a disk, a supramolecular macrocycle, supramolecular disk, which then can undergo columnar association, as you will see in a moment. Other type of entities have been much studied, like, for instance, the rosettes, where three units undergoing on each side of their, on each face of a six-membered ring, hydrogen bonding with the partner, the same units. They form these rosettes, hexameric rosettes, which have been much studied, for instance, by the group of David Reinhardt in the Netherlands, melamine and cyanuric acid units, and one can make lots of very interesting things with these. Now, what does it mean? What is it really schematically? It's a sector, which is the basic unit here, or the melamine or the cyanuric acid, which then forms a disk, and the disks can then pile up, forming a discotic supramolecular column. So that's a sort of a discotic supramolecular liquid crystal. Sometimes, not always, liquid crystal, of course. So the self-organization is the molecular sectors, they form a disk, and then the disk can self-organize into a column. So it's a stepwise type of assembly. There are many areas one can then develop, and looking at the most important thing, as you realize, is there are two main things. One is the interaction group. The other one is what is between the interaction groups. Now, in this case, as you can see, one can use the hydrazino analog of urea, which is a very interesting molecule for all these reasons, because it has many hydrogen bonds possibilities. If you condense it with an isocyanate, here ditetrabutylphenyl isocyanate, also for solubility reasons, you get this entity here. Now, this has a very interesting property, because nitrogen bonds of hydrazine, they orient in a perpendicular fashion around the NN bond. You have two-dimensional possibilities. You can make hydrogen bonds in a plane and also hydrogen bonds perpendicular to that plane. That's an interesting property. These hydrazines, they are known to form a perpendicular arrangement, or more or less perpendicular, I mean a twisted, let's say, arrangement around the NN bond. So this, we wanted just to document that by making a simple derivative, the one you see here, which one can crystallize. For instance, from DMSO, there's a molecule of DMSO, and here we're taking away everything except the core unit. You see that indeed it is organized in a perpendicular fashion, and one can then, you have a hydrogen bonding network, one can analyze its high-density hydrogen bonding sites. So this unit is quite interesting. It's very cheap, but it provides many interactions of supramolecular type, of course. Now, if you want to make it flexible, soft matter-like, then you can introduce a dimethylsiloxane chain between the bis isocyanate cyanide, and then you use again the urea, this amino urea derivative, and then you get this the supramolecular entity. You get a chain which is covalent, but here the site interactions are supramolecular, and you can then have properties which are like self-healing. This is one of those things which had been made. One of these materials, you cut it in two, you just press it together, and the section is healing. Now, another type which was interesting, you will see why this becomes quite interesting, combining lateral, using this urea, this different type of hydrogen bonding units, and looking at then lateral interactions, and trying to make films out of them, which should be, in principle, could have the property of being transparent films. Now we look at this this monomer here with the isocyanide again, and here hydrozides. It's not a urea, but it's a hydrozide, CONH-NH2. They can polycondense, make this polymer, which have a high density of hydrogen bonding sites, which are in several functional groups. A bis acyl hydrazine, so that's the hydrazine, with two acetylation CO carbonyl groups, carboxy groups, and another one, a subunit of that is a urea. This is a urea unit, and another one is a urethane. So you have a very high density of hydrogen bonding sites. Now, if you do that with a specific bonding units between, for instance, they just choose the units you want to put between, for instance, this one here, where you have 4 CH2 groups, and then you can get interesting materials. This is a film made by Dr. Nabarro Roy when he was in my group. This film is a very nice transparent film which you can make from commercial materials. No secret, nothing special. Just you have to choose the right commercial materials, and then you get this very nice film, which you can then cleave and cutting it and superposing the two ends, pressing with your finger, and you press just with your finger. That is technically not very advanced, I must admit, but it works, it's sufficient. pressing with your finger, and then you can stretch and it sticks. And this takes a few minutes. And after 2 years, the films still work, they still do the same. These are just some data which I don't want to get into. Now, the reason why I mentioned that date of 1990 when we introduced the area of supramolecular polymers, it was because it happened that 23 years later, a small company in Eindhoven has produced materials which can be used as biomaterials and biocompatible polymers, so that out of these materials and developing them, it was possible to make polymers which can be used for medical purposes. And this was the Xeltis company in Eindhoven, which developed these biocompatible polymers for cardiovascular implants. And they were used for the surgical treatment of children having a severe cardiac malformation and needing cardiac reconstruction. This was done in 2013. I usually like to point this out, that when you want to use something in a human body, of course, there are many hurdles, many conditions which have to be fulfilled. And so as it takes a long time. But in 2013, this compound, a supramolecular polymer entity developed by Xeltis, was used for reconstructing the heart of a young girl. You see her here, Dominika. She was at that time 4 years old. This surgeon, Leo Bekiria, the implantation was done on October 23, 2013, at the Bakulev Scientific Center for Cardiovascular Surgery in Moscow. And she looks very nice, very cute, and she looks very happy too, and we were extremely happy to see that at the end of it, something which we had just started because it was a nice new type of polymers one could study, to see that this could be developed thanks to the work of many people who developed the polymers, and then certainly also the work of the surgeon who dared to do it after many experiments, of course. This was then realized, and many more children, now more than 10 now. I don't know how many now, because this is a slide which is rather old. And they developed also heart valves, which are a bit more difficult to make, of course, because they have to move. And so the polymer has other properties. And it was done, and I implanted it in Budapest, Krakow, and Kuala Lumpur. So that was, of course, also a nice illustration. I like to use it also for general public lectures to tell people, look, basic research is absolutely necessary. Of course, I preach here, people who are convinced of that. But for the general public, they have to realize that basic research is very important. It starts that way, but it can take a long way to be then used, especially if it has to do with introduction into a human body. Now, what about coming now to dynamic covalent polymers? For that, you have to choose basic reactions which can be used, and one emblematic one is the condensation of an amine with a carbonyl to lead to an imine with generation of water. Of course, that's very well known, and there is nothing very special. And you can do then, you can make the imines simply. You can also exchange then, you see this, you can exchange the RNH2 and the other one, the BCO. Also these entities can be, you can have another amine, another carbonyl, and so on. You can also do the reaction by the NH2 adding to this place, this carbon here, making an aldimine, and then this can exchange also the groups. This is one way. And imines, of course, the formation of imines is something very important in organic chemistry, also in biology, less than organic chemistry, but nevertheless, it's also important in biology. And of course, there are plenty of amino groups in biology. Another reaction we discovered rather not so long ago, it's already 10 years, but it was a very interesting special exchange reaction, which is based on a derivative of barbituric acid, a Knoevenagel derivative that is called this one here, which then can react with an imine also, but in a very different way from the top. In the top here, you can either have to dissociate and reassociate, or to react one amine with an imine and make an aldimine and then go back and forth. But here, what happens is that the imine interacts with the barbituric acid, the Knoevenagel reagent, forming a four-membered ring, as shown here. And now the four-membered ring can cleave either by 2,4, which is just going back. It's a silent process, or by 1,3 that exchanges then the components. Now, what I wanted just to here to stress also is that in the classical metathesis chemistry, a four-membered ring is formed in which one corner is a middle ion, a middle center. Here, it's a purely organic metathesis, and it works very well. It's very fast. This was, in fact, found at the end of the thesis of one of my co-workers from Thailand. She is also a professor in a university in Thailand. And we found quite interestingly that this exchange reaction is very efficient. So what can you do with this kind of molecular covalent dynamic polymers? You can try to make plastic materials. Nowadays, one talks a lot about about destruction of plastic materials, about the fact can one disintegrate them so as not to let them sit around in the environment and all that. And in fact, the design was to take a piece of a polymer, a small polymer unit, and to fit it with functional groups which can lead to an imine. And this, I come back to that in a moment. So if this is a biodegradable polymer and you have imines which link those together, then in water, there is a disintegration is possible. If you dry it, it will recover because it recombines. The water disintegrates, but if you dry it, it can recombine this imine bond. This is a chemical degradation. And once it is degraded into the piece, the biodegradable polymer, then it can undergo a biodegradation. So it's a double chemical, biological degradative material. It was done in collaboration with Mitsui Chemicals. This company was very interested in supramolecular polymers, and they were sending collaborators to my group. We were developing the basic chemistry of it, and they would then look at it and see if they can do something. And as you can see here, they made quite a nice here, 300 kilos of this dynamer film, which results from a dialdehyde, a diamine, making a polyimine. And this polyimine, as now I come back to what I said earlier, the imine bond can be cleaved by water. The bond in the middle can be chosen to be a biodegradable one. So one has a double disintegrative dynamer, which, okay, nowadays it's nice to call something green. People like that kind of stuff. So these are sort of green plastics. Unfortunately, this was still more expensive than the normal kind of plastics one now uses. For instance, like polyethylene, this was more difficult and has other properties. So I think in the future, if we want really to make disintegrative polymers, I think it will come back, I'm pretty sure. Now, there's just an example. If you take this I don't tell you about all the details, but if you take one of those, sorry? Yeah, if you take this biodegradative polymer and but no imines, if you put it into water, then you get no change after 6 hours. If you put a certain density of imine bonds along the chain, then after there's a molecular weight of 6,300 between two imines, then you get a disintegration, in partial disintegration after 6 hours. If you now increase the density of imine bonds, it is completely disintegrated in the same time, 6 hours about. So this shows that, in fact, the advantage of these these dynamic polymers is also that one can regulate the disintegration, the rate of disintegration. And this can be a very interesting property for a number of applications. Now, let me just illustrate some of this data by one which is especially interesting and which can be shown quite nicely also optically. Suppose you make two films, one having a diamine A and a dicarbonyl B, making the AB polymer, and you make a film out of it. Then you take another diamine A prime and another biscarbonyl compound B prime, and you make a material A prime, B prime, A prime, B prime. You make a nice film out of it. Now you superimpose them. What is quite obvious is that since this connection here is supposed to be dynamic, that means breakable and reconstitutable, then if it breaks in one film and in the other film at the interface, and two new combinations can appear, those who were not present at the start. That means A can connect with B prime, A prime can connect with B. And this, of course, then, if it's an imine, can lead to polymer blends, but I will illustrate it to you by an optical property. Suppose you make this film based on imine formation, a polyimine film. If there is some kind of an optical property, you may be able, perhaps, by recombination through the interface between the films, to generate the other two combinations, as I've just shown you in a moment. So if you take the two films, the AB film, the A prime, B prime film, and you superimpose these films in some way, for instance, here by a corner, then at this space, exchange can occur, and the two new combinations can form. The A can connect with the B prime, and the A prime here can connect with the B. If one of these two new combinations has an optical property, like a color or like a fluorescence, you will obviously see it. Something will happen. And so that's a nice illustration. As you say, seeing is believing. So my Japanese co-workers, they made a little picture, the head of a cat, where the head is AB, the ears are AB, inside of the ears it's A prime, B prime, the eyes, like also the whiskers, the mustache of the cat, are also A prime, B prime. So you superimpose and you heat and you get changes, yellow color and fluorescence, only where it is superimposed. And this indicates that you can then make polymers which change their properties, here optical properties. One can do it also with mechanical properties, with the mechanical properties of the polymeric entity. And in principle here also, we have not exploited that, but one can suggest that this is a way to write information also. If you put two films one on top of the other, you can write with a heating laser. And if you make a stack of them on top of each other, then you can write in 3 dimensions. This is just to give an illustration. Now, an interesting unit, I have already insisted on this but this bis amino-urea or the bis hydrogenocarbonyl unit this can have, on one hand, hydrogen bonds through the NHs, like a typical urea, or also through the main chain imine. So it's a combination of a double dynamic unit, which is orthogonal. The covalent dynamics is one way, one direction, and the non-covalent dynamics is the other direction, vertical. The one is horizontal, the other one is vertical. So it's a not orthogonal double dynamic subunit, which can form H bonds in plane, and sorry, this depends now. H bonds can be perpendicular to the plane which contains the imine functions. And so this is the kind of interaction which is very classical for ureas. So H bonds and imine functions, it's a double dynamic type of unit, covalent and non-covalent. Now, I have no time to get into metallo-supramolecular polymers, which are of course quite interesting also because you can introduce metals into polymers quite easily. And in order, of course, there's always the problem, if the resulting unit which binds the metal, here, these yellow units, which can be connected, here we have a double coordinating monomer with a metal ion, which then is the connector between the this double coordinating unit. Then you get a cationic metallodynamer. Okay, but maybe it's more interesting to have it neutral, and then you can use a combination which is a pyridine derivative with the carbonyl here, and then you can make this imine here. And now you can have here, if the, for instance, if the X is H, the X is H, this is ionizable, so that you can ionize it, and with two such tridentate units and a metal ion of hexa coordination, then we get a neutral center, which makes metallo-supramolecular polymers neutral and therefore soluble in organic solvents also. So that could be quite interesting to introduce metal ions. It's a simple operation, you just add the metal ion and you get your connection. Now, I haven't time to get into that. We did quite a lot of work on this, but it's published. Now, let's come to adaptation. All this is just the introduction of supramolecular polymers, of covalent, non-covalent dynamers, covalent dynamers. What about now adaptation? Adaptation means that these objects can undergo variation in their constitution depending on some agents you can apply. And you can, of course, change the medium, change the phase from water to organic, for instance, physical stimulus like heat, or perhaps pressure. Electric field, we did some with electric field. You can apply the electric field. You can change also the type of entity you get. You can adapt it. Physical stimuli, chemical effectors, of course, protons, metal ions, other molecules, or even switching processes, changing in conformation. So these are adaptive chemical systems, and I will finish with the one which I am now quite excited about, which is the fact that self-organization can be a factor, can be an agent for driving the system to select specific units, components. And I will show you an example at the end. Now, let me first give you a first example of how this works and what is the basis of it. Here, together with Professor Paolo Samori and his group, we did the following experiment. You take this aldehyde, long chain aldehyde, and 3 diamines with C2, C6, and C12 between the amino groups in solution. And this you mix together and you look at it in the solution by NMR to see what you get. What you get is uninteresting, not very exciting at all. You get a statistical mixture of monoimines. That means you don't even have a full reaction. You have in your solution these monoimines, which you see here, C2, C6, C12, and a small amount of the doubly condensed units. So, okay. But then you do something which is really extremely simple. You deposit a drop of this solution on a surface of graphite, and you visualize it by scanning tunneling microscopy. Now, what do you see? Something very nice, a very organized layer of only one bis imine. This is, in some respects, very dramatic. you start with a mixture of incomplete reaction, and by simple deposition, this is transformed into a nice lamellar layer of only one of the initial entities. This means that the simple adsorption on a surface has led to the formation of a reaction, of a complete reaction, and to the selection of the components in simply due to adaptation to the surface adsorption. So the simple adsorption forces have done the job of completing the chemical reaction and of selecting the chemical components. Now, that means that the self-organization of the layer on the surface is the unique, the only physical force, but it is sufficient to drive the reaction and to drive the selection. It's quite astonishing, I would say. Of course, once you have seen it, it's quite obvious. But one has to realize that that is also, here I'm pushing a bit the thing, but you will see I will do it the second time also, which is that if the simple adsorption on a surface drives a reaction and selects components, that is an important step in the formation of more and more complex states of matter. Now, let me go back to a case where one can illustrate the selection as a function of the medium. Look at this monomer, a hydrophobic core with two carbonyl groups and the hydrophilic side chain R hexaglyne. So that makes it soluble in water, although the hydrophobic core doesn't want to touch water. That means that the contacts between water and this hydrophobic core will be minimized thermodynamically. So first we condense this with the same thing, except that now it's a hydrazide unit on each side, which when you make it, then this gives a polyhydrazide for this of this polymer, which is shown here, and which is a helical rigid rod. I did not represent the side chains, the R chains, they stick out. Now, this is something we studied in more detail, and it's quite an interesting polymer, which has an inverse temperature dependence. As you heat it, it gets bigger and not smaller, and that is due to hydrophobic effects. Anyway, this is not what I want to talk about here. The important thing is that we say, okay, that's maybe an interesting polymer, but so what? So what? This. If you now add something very simple to this initial mixture, where the only difference is that you use a bis hydrazide, which has now a phenyl ring, except instead of the carbazole ring in the middle, the carbazole unit. Okay, you say, all right, so okay, you mix it, and what happens? What happens is the following. If you take 1, 1, 1 stoichiometrically, 1 for the dihydride, 1 here, and 1 here. Now, if you operate in water, and as I said, the flexible side chain makes these things soluble in water, these compounds, then, of course, the hydrophobic effects will still operate. So you see nothing else than when you mix those together, you get the same polymer, the rigid rod, helical rigid rod, as we had earlier, and the other one is just not incorporating. So, okay, so sure, that might mean that hydrophobicity has an effect, but how can you prove that? Very simple. You add to this aqueous solution a water-soluble organic solvent like acetonitrile. And as you add more and more acetonitrile, you get closer and closer to organics and away from pure water. And what happens is that you get a decrease in the selectivity. In other words, more and more of the small one are incorporated into the final polymer, and at 80% acetonitrile, you get about random incorporation of the small and the large. In other words, the selectivity directed by hydrophobic effects has disappeared as you transform the medium from purely aqueous to more and more and more organic. So it's a selection which leads to adaptation of the system to the aqueous environment, and of course, when you go away from the aqueous environment, to these mixed units. Excuse me. So now these dynamers can also be of biological type, and I don't want to get into details, but just mention that we have made the analogs of biopolymers for nucleic acids, for peptides, analogs, proteins analogs, and carbohydrates. Now these do work well. You get these dynamic analogs of the biopolymers, and I think there's still a lot to do here with